In a previous video, we showed you how Zenium made it possible to give this fun go-kart an electric vehicle dashboard with IoT connectivity in just a matter of days.
Recently, we were asked to integrate artificial intelligence and deep learning into Zenium. Since this was our first AI project, we picked a modest goal of creating a self-driving car. A crazy idea? Maybe for those unfamiliar with Zenium.
Zenium is a powerful componentized software development and deployment framework from Imagine Communications. It has been powering the media industry for years, and today I'm going to show you how Zenium made it possible to produce a self-driving vehicle in just a matter of weeks.
We weren't about to take the go-kart out onto the streets with traffic for this project, so instead we decided to teach it to drive by recognizing colored pylons. Red pylons on the left, green pylons on the right, and the rules of the road were set.
The go-kart required a few modifications for our project. We needed a front-facing camera to see the pylons, a way to sense the steering position, and a motor to control the steering. Thanks to reusable Zenium components, integrating these new aspects of the kart in our Zenium blueprint was a breeze. The web camera video stream was supplied by an existing Zenium capture component. For our embedded IoT project, we had already integrated a Raspberry Pi computer on the go-kart and wrote a Zenium component to talk I2C to this ADAC chip. By reusing this Zenium component, the steering feedback functionality just required us to hook up a wire to the ADAC click shield and then configure the Zenium component to read this pin as an analog input. Now we had steering information in the graph. Controlling the steering motor from Zenium was simply a matter of configuring some output pins on the ADAC component and hooking them up to the motor controller on the kart. We configured a steering feedback control system using Zenium components, and the computer-controlled steering was functional. Now our go-kart was ready to receive its brains. Recent advances in the field of AI and deep learning are truly amazing. We hope to use deep learning to solve two difficult problems in our self-driving vehicle. The first problem was to recognize these pylons in the camera's streaming video. The second problem was to actually control the steering in real time while the kart is driving through a pylon course. For the first problem, we investigated a popular neural network for performing object detection and recognition, called YOLO, or You Only Look Once. The YOLO neural net was designed to find and recognize objects in an image or video stream. We integrated a deep learning library called DL4J into a Zenium plugin, and then exposed object detection in a Zenium component so we could experiment with its capabilities. In short order, we had the YOLO neural network detecting video stream objects within Zenium.
Unfortunately, the types of objects that the YOLO neural net is programmed to detect did not happen to include our red and green pylons. But by leveraging the integration with Zenium, we were able to reprogram the net for our own purposes. Now it was able to detect the colored pylons in the scene.
With the pylons being detected, we were on to solving our second deep learning challenge, teaching the kart to drive itself. We created a brand new neural network that would learn to drive the kart. And, like a parent teaching its child by imitation, we set up some pylon courses for us to manually drive the kart. While we were driving, a Zenium blueprint recorded the pylon information, our speed, and steering positions. We then fed these recordings into another Zenium blueprint that actually trained the neural network, or the brain of our child, with how to drive the vehicle given the observation of its environment. With the neural networks trained, we were ready to test our autonomous vehicle. We configured our neural processing blueprint to receive the video stream and steering telemetry data from the Raspberry Pi. This data stream was augmented with the detected pylon positions, and our driving neural network gave real-time updates for the desired steering direction, which was then sent back to the Raspberry Pi, where its Zenium blueprint would adjust the steering. We figured that our 200-pound child needed to show it could walk before we let it run. So we tethered a kill switch to it and watched what it would do. Even though we trained with pairs of red and green pylons, the neural network had no trouble interpreting what to do with single red or single green pylons. We untethered our child and let it run free. Okay, we still had a remote kill available in the Zenium web browser interface using our phone. After all, can you really trust a child? A working autonomous vehicle in a matter of weeks. Utilizing the power of Zenium throughout the process is what made this project feasible. Zenium not only drove this go-kart, but Zenium is truly what made it possible. I guess our goal wasn't so crazy after all.